Okay, let's get started. Uh, Thank you for joining this afternoon. Just going to give kind of a brief overview of about the radar, particularly our Weather Service radar, the WSR 88D. And we're going to talk a little bit about the basic products that you can view from that. A lot of this information now is online and in various apps, so it's out there, and you may be looking at it wondering, how do I interpret all this? And so we're going to give just kind of a quick overview on some of the things we look for at the National Weather Service when we're trying to decide whether to warn on a storm, for example. Now, I do want to say as we go, if you do have questions, you can either type them in as we go, or we'll definitely take questions at the end. The presentation portion should run just a little bit over an hour, maybe an hour and 10 minutes. And that will leave 20 minutes or so for any questions you all may have. So let's go ahead and get started. So first off, what is radar? Radar stands for radio detection and ranging. The history of radar is very interesting, used in wartime, for example, to track aircraft. And one thing they noticed in those early uses is that weather features would often obscure what they were looking for, aircraft, for example. So, it became pretty obvious that radar could be very useful for weather as well. And the way our radar works, the WSR-88D, it's a pulsed Doppler radar. So what that means is it sends out a pulse of energy, like shown in this animation. And then it goes into listening mode and listens for the bounce back or the echo. So a portion of the energy is scattered back to the radar, and the time it takes for the pulse to go out and back lets us know where the target is. And the amount of energy return is proportional to essentially how heavy the rain is, but also the size of the target. So a large hailstone will return a lot more energy than a small raindrop, for example. Here's a look at the outside and inside of a Weather Service radar. On the outside, you've got that tower with those stairs. And on the inside, you see on the right, on the inside of that big ball up top, which is called a radome, you've got this huge radar dish. And if you look at that photo there, one of our technicians is up there in the dish. It's been shut down, obviously, the radar, but you can see it's a huge radar dish, 28 feet in diameter. It needs to be large to create a fine beam to give us high enough resolution to warn on. So it's really quite a piece of instrumentation there, driven by a large motor. And you can see the long stairways there. I've hiked up in there on occasion just to look inside when we do have the radar off for maintenance. So I mentioned that the radar sends out a pulse of energy. Well, as it's doing that, it's also making a complete scan, 360 degrees around. And it starts at 0.5 degrees above horizontal. So it's not shooting straight out, but just a little bit inclined at half a degree. And after it goes around one complete revolution, then the scan angle changes and it goes up to 0.9 and then to 1.3 and so on, all the way up in precipitation mode to 19.5 degrees. And you can see this animation kind of shows what we're talking about. Basically, it's making cuts in the storm at progressively higher and higher levels, and giving us sort of a three-dimensional view of what the storm looks like. Now, when it's a clear day like today, we put it in something called clear air mode, where it's turning slowly and taking data, but it's not really stressed a whole lot. If we're in severe weather mode, then we are really working that radar with a lot of different cuts happening fairly quickly. The complete cycle and precipitation mode going from 0.5 to 19.5 is about 4.5 minutes at the fastest. So I mentioned Doppler radar. What is that? I mean, what does Doppler radar give us that conventional radar does not? Doppler radar allows us not only to detect where the targets are and, for example, how heavy the rain is, where there's hail, mapping out the energy return all around us. It also gives us velocity. It gives us how are those targets moving? Are the raindrops moving toward or away from the radar? And it uses something called a Doppler effect, which is basically what happens is the frequency of a wave depends on the motion of the source. So we've all experienced this, maybe without realizing it. If you've ever heard a siren on a vehicle approaching you, and then it passes you and starts moving away from you, you notice the change in pitch of the sound wave in that case. And so basically, when a target or a source of a wave is moving toward you, you hear you observe a higher frequency than when it's moving away. So for a sound wave, you hear that pitch change. Same thing for a train horn. It's coming toward the intersection, you hear a high pitch, it's moving away, you hear that drop. So this is the Doppler effect. The radar uses this to determine, in the case of the weather radar, are the raindrops moving toward or away from the radar? And by doing this, we can map out circulations and motions within the storm. So the radar is a great tool, but it does have limitations. One, if the storm is far from the radar, say greater than 60 miles or so, but even more so if it's greater than 100 miles, then we have an overshooting issue where the height of the lowest beam might be up 10, 11,000 feet, even 13,000 feet in some cases. So we're not getting much information below that. And we call this limitation overshooting. Interestingly, if the storm is too close to the radar, for example, if it's right here at the Weather Forecast Office here in League City, then the radar is of little use as well, because we're too close. In that case, the 19.5 degree cut is not really extending very far up in the storm at all. So we're missing things up in the heart of the storm. So in a case like that, we need to look at surrounding radars. And in all these cases, we rely heavily on spotter reports and EM reports of severe weather, may come from dispatch as well, to kind of fill in any sort of gaps, any kind of details. So that's a really critical part of the warning process that you all help us with. It also is important to look at the closest radar to get that low-level detail, and that's what the image in the lower right is meaning to show, that you're seeing low levels in the nearby radar, but in the more distant radar, you're not getting that useful low-level information. So here's a map, basically showing the different radars, the different 88D radars in Southeast Texas with the different radar IDs. We're HGX here in League City, but you can see we've got Granger, GRK off to our northwest. EWX is Austin, San Antonio. Shreveport, Fort Polk, and Lake Charles also shown. Now the shading is interesting. It shows the height of the lowest beam from any radar. And so if you look at that, you look at Harris County, you've got different shades of blue. What it's telling you is the height of the lowest beam is somewhere between 1 and about 3,000 feet above ground level. But if you go up to, say, Houston County, up near Crockett, where that county is sort of in between all different radars, there the lowest beam height is more like 14,000 feet above ground. So there we have more of an issue, really. If you look at Houston County, Trinity County, and Polk County, there is not as much low-level coverage from these radars. The other thing I want you to note is for the Bryan College Station, Caldwell, Burleson County area, for example, The closest radar is not HGX, it's actually GRK. So we're going to lean heavily on that radar for storms in that sector. We're also very fortunate here at the Houston office to have access to terminal Doppler radars. You can see a photograph of one there out at Charlotte. The terminal Doppler radars are really designed for takeoff and landing at major airports, and we have one of these at Hobby and Bush. And they actually have a lower elevation scan, and we get data more frequently. So it's really tuned for the needs of the aircraft, but it's very useful for us as well to supplement what we're seeing on our 88D radars. So to have two in our area is really beneficial to our warning operations. Also, I want to note there are private companies now that are putting up smaller radars in different areas. And so on the lower right, you can see one small radome on top of a water tower. And so that's an effort that's ongoing right now. We at the Weather Service do have access to this data at this point. That's kind of a recent development. And so we're kind of evaluating it, but we're looking at any data we can have. The Texas A&M University Meteorology Department over the years has run a Aggie Doppler radar, an ADRAD, and that's been so helpful for some of the events we've had up near that area. So just to kind of review and refresh some of the concepts we've been talking about. The radar is undergoing a scan strategy starting at a low elevation of 0.5 degrees and then incrementing up to about 20 degrees relative to horizontal. The radar does have limitations both near and far from the radar. Very close to the radar, we're dealing with something called the cone of silence, where the highest available elevation cut isn't really extending into the storm very much at all. And at far distances, we have overshooting of the lowest beam. And so those are two limitations that we have to deal with. And I didn't mention this also, the beam actually becomes broader as you get farther away from the radar. And so that has implications for resolving circulations and other smaller scale features. If, for example, there's a circulation that occurs within the beam, it doesn't extend to more than one essentially a beam, then we're not resolving that circulation very well. In fact, the inbound and outbound in that case, like we see in the middle circulation here, would sort of cancel out. So all those limitations are meant to, again, point out the need for reports, preferably real time, but even the next day, very helpful. And you'll hear from me sometimes saying, hey, we had a storm in your area. Can you tell us what you know about it? You know, did it produce hail, any sort of damage? And the emergency managers in general have been great at ferreting out that information and getting it to us. So a little bit about the radar there, and let's talk now about the different things the radar measures and products that we use to make warning decisions. These are the types of things you may see on apps or online or even on the television broadcast. The returned energy is basically plotted as reflectivity. That's probably the most familiar radar field. You can see it in this slide on the upper right there. The dark areas, red areas rather, indicate heavy rain. The green, light rain. The yellow, moderate rain. If we were to see some purple in there or even white, very high reflectivity, that may in fact be hail. Mean Doppler radial velocity, sometimes that's basically how the targets are moving, how the raindrops are moving relative to the radar toward or away. So in this example, we can see some bright blues and some next to some reds with the radar situated off to the right and that is in fact showing a circulation within this southern cell. There is something too called spectrum width, which I won't talk a whole lot about, but it can be useful as well. It measures the dispersion of velocities within a radar sample volume. So for those circulations that are so small they're not resolved well by the radar, sometimes you'll see a spectrum width maximum. So you know, this would be used less often, but it still can be useful. Another thing you may see out there is something called storm relative velocity, or sometimes storm relative motion, SRV or SRM. All this is the base velocity, but with the motion of the storm subtracted out. Now, why would you want to do that? Well, it turns out especially for faster moving storms, the motion itself can lead to sort of asymmetries in the display. So if you look at the example on the left, I've got a storm moving away from the radar. I've got strong outbound next to weaker outbound. That's what the reds are showing. But if I subtract out the storm motion, now we have a more symmetric vortex. So it can be easier to recognize circulations in the storm relative motion mode. Honestly, we look at both SRV and base velocity, but in this case you can see with the greens next to reds how that circulation, what we call a mesocyclone, really stands out. Here's a look at a hurricane example. Hard to believe 16 years ago we had Hurricane Ike, and it was a direct hit from a Category 2, large Category 2 hurricane. You can see the reflectivity in this case showing a local minimum over Galveston Bay. That's the eye of the hurricane, of course. And then on the Doppler side, I put the location of the radar here with a little radar symbol. You can see the light blues indicating raindrops essentially blowing toward the radar, and on the other side of the radar, the yellows showing a strong flow away from the radar. And now this is the radial component of the wind, and if you sort of connect the maximum inbound and the maximum outbound, it gives you an idea of the direction of speed, the direction of the velocity rather. So the bright blues, you go to our color table here, we're looking at 70 to 80 mile per hour winds in this zone toward and away, sort of coming from the north-northwest as part of this western eye wall. So there's a hurricane example. The Hurricane Center is looking at this radar data when the storms are approaching landfall to try to estimate that wind speed as more of a direct measurement. Here's a thunderstorm example. You can see here, this is up in the Dakotas. I've got the radar looking at these storms from the east, looking west, and we've got 1, 2, 3, at least 4 thunderstorms here. One seems a bit stronger than the others. And so I look at first my reflectivity. I'm looking for patterns in this case. And there's a couple of things that let me know this is a supercell. I'll go into more detail of that later. What I've circled here is what we would call a hook echo. You can see it looks kind of like a fishing hook there on the rear part of the storm. Storm moving from south-southwest to north-northeast. The other thing I want to point out here too is on the leading edge, you see how it looks a bit like a V. You know, we'll come back to that later. Sometimes that's called a flying V signature or even a flying eagle. If I look over to the Doppler part of the Doppler radar, look what we have here. We have bright red next to blue, very tight, strong circulation, outbound next to inbound relative to the radar. So I've got a circulation there, I've got a hook echo, I've got a supercell, and this is what was going on at the time. Now, so we've talked about the base data. There are other radar products that are created after the radar has gone through a complete cycle. In other words, it's gone from the lowest cut to the highest cut, and then it's starting over again. Well, at that point, the radar has a computer tied to it, and it's doing some calculations and plotting some maps of these derived parameters. We've got composite reflectivity, echo tops, essentially measuring the altitude, the height of the highest parts of the storm. We've got something called a VAD wind profile, which is a measurement of the vertical profile of the wind. Of course, precipitation products are front and center when we're in flood mode, trying to get estimates of rainfall based on the radar reflectivity. And then there's algorithm output, which I'll show you some examples of. There's a hail algorithm, mesocyclone, and a prob severe. Basically trying to take all the data and run some algorithms to give us an idea how big is that hail, where are the circulations, and what's the likelihood of severe. So the automated part of this is mainly to kind of draw attention to certain areas the forecaster can look at more closely. Composite reflectivity, basically this slide explains what that is. A lot of times you'll see something called base reflectivity, which is usually the lowest angle cut, the returns at that angle showing what's going on closer to the surface. But what the composite reflectivity does is it looks at all the cuts, and what it plots on the map is the maximum return or the maximum reflectivity from any of those levels. And so you can compare the two here, composite versus base. And why this is really good is a lot of times the first echoes will be up in the cloud, and a lot of times the hail will be forming well up in the storm as well. So we'll have an early indication that there's hail up in that thunderstorm by looking at composite reflectivity before it descends down. And so it gives us a little bit of an extra heads up. This vertically integrated liquid has some similarities. Essentially what it's doing is it's taking reflectivity at all those levels, and it's basically adding them up. It's converting the reflectivity to liquid and then summing that up. So when a high vertically integrated liquid, or VIL, indicates a very intense core of rain and perhaps hail extending through a deep layer. And so those two together tend to really draw out storms that may have large hail, among other things. So the VIL is, again, a tool that's been used ever since the 88D was rolled out in the early 1990s. I mentioned the precipitation products. We can get displays as far as hourly precipitation, 3 hourly, storm total. And again, it draws our attention to areas where we have a flash flood concern, for example. Here's just an example of a storm total rainfall from the tax day floods of April 2016. Kind of remarkable to see the rainfall differences on either side of I-10 in that case. That was the bullseye for that rain event. There are other radar products that we haven't covered that are now available with the advent of dual polarization. Our radar underwent an upgrade, I believe, in about 2014, where beforehand, if you look at the left-hand side where it says conventional radar, the beam essentially would be oriented horizontally, peaks and troughs. It would go out with a horizontal, and it would return information on the horizontal dimension of the target. What dual polarization means is we now have horizontal and vertical polarized waves going out. And therefore, now we're getting not only the horizontal dimension, but the vertical. Okay, so what that means is instead of only giving us an idea of the size of the target, now we have an idea of the shape. And if you look at the radar example here, a raindrop is going to look a lot different than a hailstone, which is going to look much different than a snowflake with this dual polarization radar. Here are some of the data fields with this dual pol radar. Differential reflectivity is the ratio of the vertical to the horizontal component, or rather the horizontal to the vertical. Gives an idea of the target shape and also what it is. Is it a large raindrop or a hailstone? It can actually help us make that determination. Correlation coefficient, this is kind of interesting. This is giving us an idea of how uniform the targets are. Is it all rain that the radar is observing? Or if it is, then our correlation coefficient will be near 1. Is there a mix of rain and hail? If there is, then the correlation coefficient would be below 1 because the correlation between the different targets is going down. There's another use for this I'll show in a moment where we can actually spot debris being lofted by a tornado using this tool. And then differential phase, I won't talk a lot about that, but that tends to be tied to precipitation type and intensity. Now, I just mentioned that we can actually infer debris getting lofted by a tornado. If we have these 4 things together, high reflectivity, a strong inbound-upbound couplet, or a mesocyclone, and a correlation coefficient hole or dropout here, low values, along with differential reflectivity on either side of 0, meaning sort of tumbling debris. If we have these 4 things together, we refer to this as a tornado debris signature. And you really do need these 4. The differential reflectivity, maybe not every time, but every other thing you need all elements of that to have a true tornado debris signature, or TDS. So what is the forecaster doing with all this data? Looking at multiple tilts, sometimes in the form of multiple panels or vertical cross sections. We're looking for things like circulations or mesocyclones, which may imply supercell storms and tornadoes. We're looking for high reflectivity cores aloft, which may precede large hail events or even downburst winds. And of course, we're looking at precipitation data to highlight areas where we're concerned about flash flooding. So that's basically what's going on. And we've got new data coming in continuously with these volume scans repeating every 4 to 5 minutes. So you can imagine if you have multiple storms, multiple hazards, flooding, hail, tornadoes, you've got several people engaged in putting these warnings out. All right, so let's get into some examples. First off, let's talk about supercells. These are the most severe types of storms. So in the lower left, imagine the radar is at position position R, excuse me, and looking off to the northwest. So on the reflectivity end of things, the storm's moving from southwest to northeast. I've got sort of a broad area of light to moderate precipitation on the forward flank. And then as you work your way down, this red area is where you might see some large hail tucked in there. And then there's a bend by the time you get to the right rear of the storm. That's where your tornado could form. There's also on the Doppler side of things, outbound next to inbound there's your strong mesocyclone in this case. So that's kind of the classic look at what these storms look like on radar. There's a lot more information on this map, not only the reflectivity pattern, but also some of the different phenomena going on in the supercell, where you've got a rain area here, you've got a forward flank downdraft. You can get something called a rear flank downdraft wrapping around the southern flank of the storm. And we're going to show some examples in a bit. We actually had quite a bit of wind damage around Needville and Angleton just a few weeks ago, and we believe it was probably this RFD feature that was doing that. And then some other things are noted there on the diagram. Just a visual look at what these supercells look like, comparing some of the things labeled here, the flanking line on the southwest flank, the main updraft area, kind of tucked in where we have this notch in the supercell. And visually, this is what it looks like. On the left-hand side, there's your flanking line. So these are cumulus clouds that are not fully developed. Here you've got your anvil, your overshooting top wall cloud, where near where the mesocyclone is, really more where the updraft is, than a shelf cloud and a rainy downdraft. Looking at some examples now, this is Oklahoma City F5 tornado from May 3rd, 1999. Again, fairly broad, moderate, light to moderate, even some heavy rain on the forward flank. And then you work your way down and you see that bend on the rear flank all the way into a hook. In this case, this is your hook echo. Tornado occurring at the tip of the hook. And so again, this is pretty much a classic tornadic supercell that we're looking at. The cartoon depiction up here on the left-hand side. Now, if you were to do a cross section from A to B here, you would actually see what we call an echo overhang above, where basically the air is coming in and up. This is where the updraft is. So these are kind of the classic appearances of a well-developed supercell storm, and you'll see some of this in the examples that we're showing going forward. So looking back to November '92, the ADAD was fairly new at the Houston office at this time. We had a tornado outbreak across southeast Texas and portions of Louisiana, Mississippi, a number of strong, large, long-track tornadoes. And here is an image from the ADAD. Again, it was fairly newly installed at this point. And can you all see the hook echo? Well, there's definitely one right there on the east side of Houston. I believe this is the Channel View tornado. And look right on the Doppler side of things, there's a outbound, inbound couplet. So we have the hook echo, we have the tight circulation. In fact, we have a tornado. Now you can even look back up into Liberty County, you'll see another hook echo along with the circulation. And as I said, there were several tornadoes on this day. Looking at Christmas Day 2012, and I should point out, severe weather season in southeast Texas, January through December. We can get these tornadoes and severe weather really any month of the year. There is a peak in April and May that we're heading into now. But here's a case of a really powerful tornado, Christmas morning. These two retail locations, I believe Farm Supply and so on, they were vacant on Christmas Day, thankfully, because they were pretty much wiped clean down to the slab there. Here's a look the day after. One thing we do in the Weather Service is we'll be out typically the next day to survey the damage with the emergency manager, preferably, or someone else from the jurisdiction that's freed up enough to show us around where the worst of the damage is. So what did that look like on radar? On the left-hand side, you can see a number of thunderstorms. Now keep this in mind. Houston County is again in an area that's pretty far from any radar, so you're not going to see detailed low-level features like a hook echo necessarily. But with these stronger tornadoes, the tight circulation and the mesocyclone extends well up into the storm, and so you can see reflectivity here. Can anyone find the mesocyclone in the velocity? And you can go ahead and type your answer if you can see how to do that. You can type that into the questions dialog. Tell me the nearest town to the circulation on the velocity side. All right, Jamie, I see, and Will, yep. Probably some of you are trying to figure out how to work GoToWebinar at this point. But yeah, I see a number of answers now, and y'all are getting it. Yeah, it's down here south of Kennard, and that's the beauty of this radar is, if you were just looking at the rainfall pattern, you'd be like, well, I see a big storm south of Kennard, another one between Lovelady and Crockett. What do I make of all this? Well, there it is, tight, really tight circulation there south of Kennard, in that Pennington area, and there is this strong tornado ongoing at this time. And it's nice to see some of y'all. I see a Heath there from up in Houston County, so it's good to have you on. Another really powerful tornado to impact our area in recent years is on Alaska, Polk County, April 2020. And for a lot of these, you'll see April. We've had a lot of April events. The last one, of course, was December. It's actually just setting down at this point. We had been tracking this supercell all the way from Brazos County, and just kind of hoping and praying it would make its way along and not drop this type of tornado, but it did in fact drop right along the lake shore there. I did want to give Texas Forest Service a shout out here. They did something very clever. They took satellite data, vegetation channel, before and after the tornado and subtracted the two. And what do you get out of that? Well, you get this black line that really notes the track of the tornado. Now, I mentioned other radars. We have our 88Ds, we have our terminal Doppler radars. This is actually from the ADRAD, the Aggie Doppler radar. This is the same storm that eventually dropped the tornado on Alaska. And you can see TAMU here. This is the location of the radar. Look up at this feature here. I mean, there is an incredible depiction there of a hook echo, kind of flaring out on both sides. So this is a very classic appearance to one of these. Now, on the velocity end of things, we're not seeing quite the circulation yet. So there was but there was actually a funnel sighted west of Bryan briefly. Now we move ahead in time, I think about an hour or so, and now it's moving across Trinity County into Polk County. Look at the reflectivity here. Remember I mentioned light to moderate rain on the forward flank. In this case, storm moving from west to east. Remember I said there could be hail tucked into where the pattern bends. And sure enough, this bright purple here, this is large hail. We had tennis ball sized hail at this time in Trinity County. And then sure enough, there's that hook echo kind of dangling down to the south. So people in Alaska, some of them were a little bit weather savvy, and they were looking at the radar and all this hail to the north, and they were thinking, oh, we're going to miss that. But in fact, this appendage, this hook dangling down, they went essentially straight to the tornado. So they missed the hail, but in this case, the tornado came right through. Here's the hook echo. Here's your tight circulation, yellow next to blue, very tight and bright. And then look at this, your correlation coefficient. I've got low values of correlation coefficient, or CC, and even low values of ZDR. So it really checks all the boxes for a tornado doing damage in Alaska. And I was texting and talking to the emergency manager in Polk County as this thing was approaching, and when we saw this, our hearts sank because we knew that this thing was doing damage in town, and we reported that to the EM. Another tornado, another April strong tornado, and another one up in Houston County. This is west of Lovelady. The emergency manager took us around, and you can imagine coming around the bend and seeing this type of destruction with vehicles tossed around, trees pretty much stripped down, and then a mobile home here destroyed. The only piece of good news from this scene is that the man who lived in this home was not home at the time. So what did that look like? Once again, you're getting more of a mid-level view of these storms because they're not very close to the radar. However, with these strong tornadoes, like I said earlier, they often will have a strong mesocyclone aloft, and it is definitely being picked up here, in this case by the Shreveport radar. So even though we're not seeing a hook per se, because we're hitting the storm higher up, we're getting that tight circulation. So it's very clear where the tornado is in this case. Now, one thing I didn't mention before, the Shreveport radar actually was able to configure their radar to have a lower low-level cut down to 0.3 degrees instead of 0.5. So for storms up in Houston County, Shreveport may be your best bet in Trinity County for getting the lowest level available. More recently, Southeast Harris, right in our backyard now. This tornado, a January tornado, moved through Southeast Houston, on through Pasadena, Deer Park, and Baytown. And you can see some of the damage here. This is a church with the roof and wall gone. And the people at this church were very grateful. They got the warning. They took shelter, and they were very appreciative of that. And this is an example of what I would call a high precipitation type storm. I'm going to show you a few of those. These look a little bit different than the ones we've seen up to this point. And Ollie, thanks for your question. Like I say, we'll be running through questions at the end. So take a look at this Pasadena tornado, and you'll see it looks a bit different. Now, remember, we're pretty close to the radar now, so we should be able to see low-level features, but you're not really seeing a hook echo. You're seeing kind of a big mass of heavy rain. But here, the Doppler part of Doppler radar really stands tall because I've got a tight circulation here. I'm going to go ahead and circle the areas I'm focusing on. A tight circulation here. This is Beltway 8. Here's 45. Actually crossed both of those major highways. Reflectivity is basically reveals that tight circulation is surrounded by heavy rain. All right, so I'm going to try something. I'm going to try a pointer option here, more of a laser pointer view. Can you all see my my pointer now? Maybe a bit better, hopefully. Thank you. All right, thanks for that suggestion. So yeah, as I was walking you through these different things, I didn't realize my pointer wasn't highly visible. So here, this is the area we're focusing on. Notice this tight circulation is really surrounded by heavy rain, and that fits with people that went through this storm. And I'm sad to say, I was teaching a class this day, and I sent people out early, because it was getting bad out there. No tornadoes at that point, and 3 of the people in that class actually encountered this tornado, and they may have even driven through it, and they all described the same thing. And we've seen videos, horizontal swirling rain, low visibility, moving in and moving out, high winds and damage. But so there was really no legitimate photo of this tornado. It was so wrapped in rain. Look at the correlation coefficient. You see that blue hole there? I'm going to go forward and back. Here you can see it's even tighter. The circulation has tightened up further as it's heading through Pasadena toward Deer Park. The damage is a bit worse at this point. And so it's classic. We see the tight circulation. We don't have a hook per se, but we have high reflectivity. Remember, that was the criteria for a tornado debris signature. And we have low correlation coefficient. So again, this checked all the boxes for a tornado damage signature, and we were able to put warnings out for a confirmed tornado, even though there was no sighting. The radar itself really indicates that it is indeed a tornado doing damage. Thank you for your comments, Stephen. Yes, many people encounter this tornado directly. Honestly, it really is a blessing that there were no serious injuries. We did have some injuries at a senior center, minor injuries, but given the population, the number of people that were out and about, I've seen videos from school pickup lines, things of that nature, that we didn't have more issues. It could have been worse. Another interesting supercell that produced a couple or three tornadoes, actually. Pasadena, LaPorte, Morgan's Point, March 2017. Actually, we're near the anniversary of that day after. You can see the tornado actually made a cut through some of the big container stacks there at Morgan's Point, toppled these things over like blocks. Another tornado flipped some vehicles over in Pasadena. So you can see, this was an EF1, EF2 type tornado still doing significant damage. Look at this thing. Now this looks a bit different, right, than some of the other ones we've looked at. Almost looks like a hurricane. I mean, you have this kind of broad circulation. You've got a large mesocyclone, large and broad mesocyclone. One thing I can tell you is the TDWR radar really added a lot of great detail. It actually showed little bitty tight circulations pivoting around the larger cyclone here. So basically you had tornadoes that were rotating around this larger circulation, and this is what we would call an HP supercell. A lot of rain involved. So as we continue forward, I want to emphasize these supercells come in all different sizes, small, medium, and large in this example. The smallest of the small we refer to as mini supercells. And, as you might imagine, these can be very difficult to warn for because, as I said, the radar doesn't resolve small features very well, especially as you get at greater distances. One interesting example was from Halloween 2015, where we had supercells that weren't producing any lightning. They were fairly shallow and on the small side. They may be extended up to 30,000 feet. So we kind of refer to these as super showers. And but they dropped many tornadoes across Brazoria County, up into the Alvin, Friendswood, LaPorte, Pasadena areas as the night went on. Now here's an example of some really fine detail from the Houston Hobby terminal Doppler radar. In fact, the tornado almost hit the radar in this case, but in this case, the radar is looking up at this storm. Yeah, I'm trying to figure that out. This could actually be from our radar, but in any case, we have a good close view of this, so we're seeing a lot of low-level features. Look at this hook echo. I mean, it's really striking. With the tornado on the ground at this time in Friendswood, Texas, it has the higher reflectivity, it has a tight circulation, and a low correlation coefficient. So all those features are there. So there's your tornado debris signature, 5:30 in the morning, October 2015. This is a really incredible example of a damaging tornado that hit Bryan, Texas, and didn't look like much on radar, to be honest. I'll show you the radar depiction in a moment, but you can see the track of this tornado through more rural areas, but it did hit some structures. But look at all these subdivisions all around there. So, for places that were hit, that's no consolation, but it could have been a lot more impact. You can see a still shot from a video here shared by KBTX. Here's a storage facility that was destroyed. There was a man in this facility who had a really interesting story to tell as he saw this tornado coming at him. And then I believe this is the view from the meteorology department tower. So, you can see videos of this online, but take a look at this. I want you to look at the reflectivity on the left and the velocity on the right, and just imagine where would you expect this tornado to be, or if anywhere. And I can tell you, a lot of focus was on this big, nasty line coming in where we had a severe thunderstorm warning out. But it's actually, believe it or not, I'm going to circle the area where the tornado is ongoing. It's right there. All right. So on a reflectivity into things, it looks like just a light rain shower. There is a circulation here, however, outbound next to inbound. And I can I'm not showing you correlation coefficient, but there's actually low correlation coefficient. So that debris is getting lofted into the radar. So point here, and there's another storm to the southeast of that has that little kind of bend to it. So these are mini supercells that are producing these, and you can see how challenging they can be to warn for. Bow echoes, transitioning to more of a straight line wind type signature here. This is an example of a bow echo that moved through Brazoria County, actually impacted the circus, I believe, in Angleton on this night. And so in the upper right, you see this kind of classic comma shape to a bow echo. In the lower right, you can see a typical sequence. Starts out as a cell, becomes more elongated into a comma shape and a boomerang shape. And when you see this moving quickly along, think some very strong straight line winds, kind of near the apex of the bow, near where it's bowing out. Now in this Brazoria County case, we had a bit of everything. We had straight line winds. You see the purples in there. Those are large hail reports. These high winds extended all the way down to Galveston Island. Here's just more of a close-up look at the reflectivity and the velocity from one of these. This is what we refer to as the comma head and the comma tail. This one has this really bright, these high returns extending from Danbury down to Lake Jackson and through Angleton. Now the velocity shows kind of some bright blues in here. Well, what is that? Those are some very, very strong winds working their way through Danbury. So in this case, Danbury had both very large hail and very high winds, as did Angleton and Lake Jackson. You can get tornadoes from these, but more predominant would be the straight line winds. Another example of a bow echo, this from Dallas, the Dallas area. And what we look at for these ideally is the base velocity. So that gives us ground level radial winds and the reflectivity. And what you see is kind of this bowing out that's just pushed through Dallas, plus these bright outbounds, very strong outbounds on the order of 70 miles per hour. So that's kind of a direct measurement of how high the winds might be from this particular storm, which is bowing out like we described. We had another storm up near Bush Airport where it was showing, like 90 to 100 mile per hour winds on the radar starting to come in to that area. And sure enough, the airport actually measured those types of winds. And so that's happened within the last year. Another type of radar feature to look at, storm complex, what we call a squall line. These fast-moving storm complexes, this is not so much an individual thunderstorm, but a line of storms pushing quickly through. This one produced 98 mile per hour winds, May 2nd, 1993. My understanding also is there was a boat race going on, and some of the boaters I've talked to were impacted directly by that, and that pretty much laid their sailboats down. So again, this is what we call a squall line. Now squall lines, bow echoes, you can have really both. You can have a bow echo within a squall line like we have here on the left-hand side. This is more of a cartoon shape describing the structure of the bow echo. and so on. Now you may hear the term derecho, and this is basically a long-lived squall line that can do a tremendous amount of damage. Now I've been at the Houston office since 2008, but I did spend some time up in Detroit at a forecast office there, and we would get these one day after the next, and you could see them develop in the lee of the Rockies in the evening, and you knew they'd be pushing through Michigan, around 4 or 5 a.m. So we would actually staff people up to come in expecting this derecho to push in from hundreds of miles away. This particular one got a lot of attention because it went through the Ohio Valley right through the Washington, D.C. area. And you can see in the upper right, these are all wind damage reports. The dark boxes there are high end, hurricane force or greater. And these are all the warnings in blue. So this one, actually, there were 22 fatalities from this derecho, and they can be very, very dangerous. We can get these, but they're more common up in the north. Another type of system we deal with, sometimes with these bow echoes or squall lines, we can actually get vortices along them, and we can get kind of weak, quick-hitting tornadoes along squall lines. We sometimes refer to these as quasi-linear convective system tornadoes, QLCS tornadoes, and we definitely get these around here. They can be very, very difficult to warn for. I want to show you an example of one. On the right-hand side, you see kind of a line of storms, like a squall line. But along that, the velocity data shows these inbound, outbound couplets, almost like a wave pattern there. You see that kind of extending out, so tight little circulations. And so what you see is, kind of a large area of kind of modest wind damage, but then these little small tracks within the damage paths of these created by these small tornadoes. So again, we're focusing in on this circulation here, northwest of Trammels. Even has a little bit of a hook if you use your imagination there. And then here's kind of an example where you get one form evolving into another. And so what I want you to do is look out near Laredo, and you'll see a supercell not moving, splitting, and then all of a sudden it evolves into a bow echo. And look how it's bowing out across the Corpus Christi area. So as this thing was pushing offshore south of Corpus Christi, as I recall, it had like 80-mile-per-hour winds. So the point I'm making here is you can have one type of storm kind of evolving into another. Talking about large hail now, and we have a recent hail event up in Belleville, among other areas. You can see on the upper right some of the hailstones from that storm that occurred just a few weeks ago. We look for some different things that I've mentioned there. We look for the hail core aloft initially. When we see that, and it's going to come down, we try to get that warning out as quickly as we can before the hail actually gets to the ground. We look for a echo overhang, a little typo there, something called a 3-body scatter spike, and high reflectivity from the large hail. So let me just show you some examples. This is what I mean by 3-body scatter spike. So if you're looking at the radar, looking at the storm, you see this extension out the radial from the high reflectivity. Those purples and whites, that's large hail. This little spike that extends further down the radial, that's another indication that it's very large hail. So what's going on there? The radar is hitting the hailstone. It's actually, some of it is scattering back to the radar. Some is scattering to the ground, and then back to the radar. So what it's seeing is a return that's a greater distance away, what we call a flare echo there, because you're getting multiple scattering going on. Now I'm going to show you some data from this site, and I will send these slides out to everyone, by the way. Anyone that registered, you'll get these. You'll be able to kind of look back. But there's a link here you might want to look at. This is what we call multi-radar, multi-sensor viewer. And what it does is it takes all the individual radars and creates mosaics or composite products that you can look at. And what I'm showing here is from this day, from March 16th. I'm showing basically hail size algorithm with over time. So what you see, if you look near Belleville, they had huge hail, and then the storm fell apart. The storm essentially collapsed over Belleville, dumping huge hail and high winds. It's what we would call a downburst. But look, there's another hail swath too that worked its way through Needville, down through Danbury and Angleton, and then offshore. So this second path was a supercell storm, and what I want to do is show you some more data from those areas. So here is the Belleville storm. What I'm looking at here is the reflectivity on the lowest level. I've got the whites there are pretty much top of the scale. So there's very large hail that the beam is detecting near the surface. And then if I go one elevation scan up, check this out. You see this flare echo extending out from the core. You see that? That's that 3-body scatter spike. Okay, so when we see that, we think giant hail. The velocity not really showing any kind of circulation at all. You know, anytime there is damage, people are going to think tornado, and you know, it's understandable to a point, but it doesn't have to be a tornado to produce significant damage. And in this case, really no circulation, but there's a tremendous hail core just hovering right above Belleville. In fact, this here is one of those algorithms I talked about. It's actually saying the maximum hail size could be over 4 inches from these hailstones. So I'm curious what the largest hailstones people had out there. I mentioned we look for the echo overhang. So if you look back, you see I've drawn a white line here. What you can do is do a vertical cross section using that. And so now it's showing me what does it look like aloft, not only at the surface, but aloft. And here's Belleville tucked down here. Look at this unbelievable echo overhang, very high reflectivity. This is, again, that weak echo region I mentioned. This is, remember I showed you the cross section of a supercell. You know, this is textbook right here. And so this is all large hail suspended right over town, making its way down right into town. So they just had a big hail dump right in the town of Belleville. A lot of wind with that too, a lot of damage. And if you all saw photos from that aftermath, it was, you know, the ground was really whitened, almost like snow. So moving ahead in time, looking at this this other storm, the one that moved through Angleton, Danbury, Brazoria County, extending back to Needville. What are we looking at here? On the left-hand side, I've got my that's misplaced just a little bit. That bright purple area is my hail part of the supercell. Now on the northern part, I've got my V, flying V, a little bit of what we call a flying eagle appearance up there. And then here is what you would call more of the hook part of the supercell. Remember I said rear flank downdraft. I'm going to show you evidence now of some of these higher winds that end up wrapping around the right flank of this supercell. So let's zoom in a bit on the Angleton, Danbury area. A lot to see here. I've got hail in between Angleton and Danbury. Danbury seems to be getting some of the maximum hail there in areas north of Angleton. And then on the base velocity side of things, you see this orange here. This is a radial component of velocity. We actually don't have the best look at the magnitude because it's not blowing toward the radar. It's somewhat perpendicular. But you can see this starting to get brighter, you know, showing 50 to 60 knots or 65 mile per hour radial velocity. And then we can zoom in just a little bit further, focusing on Angleton and Holiday Lakes, and you see these bright yellows here. This is a stripe of 70 to 80 mile per hour winds, basically from Angleton to Anchor down to Holiday Lakes, and then extending south down toward the fairgrounds as well. So this is, I'm fairly confident, evidence of this rear flank downdraft kind of wrapping around the southern flank of the supercell. And we did have measured winds between of hurricane force, even at the airport. So pretty impressive damage there. Don't think from a tornado, but once again, when people get this level of damage, they're always thinking tornado first. And then further on, you can see those high winds. Did I? Sound cut out. Okay. Oh, it says I'm back now. All right. Thank goodness. Oh boy. All right. You never know. All right. Appreciate the feedback. Yeah, keep it coming. If it happens again, shoot me a message. Yeah, the chat's working well. All right. All right. So last I heard, don't think from a tornado. Yes. Okay. So we're talking again about these high winds working their way down through Holiday Lakes, Angleton. Now, after we get a big wind event, we'll be out looking at damage. I remember driving from the PD there up Anchor Road toward Anchor. So sure enough, some of the worst damage was in these areas. I did have a question about purple area around Bailey's Prairie. Let me see if let's come back to that question later. So again, we've talked a lot about supercells, large hail, high winds, tornadoes from those very damaging types of storms. Let's move fairly quickly now through microburst. What happens here is the storm core basically collapsed down, kind of like we saw in Belleville. And you can get high winds, heavy rain, hail, all at the same time. The air descends, hits the ground, and spreads out, and we get that kind of damage. This happens to be damage April 2018 out at Hobby Airport. There was a hangar that was destroyed by these downburst winds. There's more of an aerial view. And so this is quite interesting. This is from the Hobby Terminal Doppler radar. The wind damage is at the red dot here. You can see the reflectivity not really showing anything in this case. But what do we have at the ground? We have air blowing in and air blowing out along a radial. This is the low-level divergence. You can imagine when the air hits the ground, it spreads out forward, and then on the backside, it spreads back a little bit, and that's absolutely what we saw on either side of that damage area. So we're pretty confident this was a microburst. There's the push out and the push up as the air hits the ground and splatters out in both directions. And then you can kind of follow that forward and see that signature. So this is not a tornado. There's no circulation. In fact, it's more divergence pointing to this this downburst phenomenon. Now, there was no warning for this. These are very hard to warn for. You can see there's not a whole lot that preceded it. So it's a real challenge for us. Huntsville downburst, again, a recent event, May 2023. Hard to believe it was almost a year ago. It seems like yesterday. And once again, a huge area of significant damage all across town, kind of in a 5-mile radius. Large trees uprooted, downed. They lost power there. The hospital was impacted. So just a very, very bad situation there. I'm going to kind of skip over this, but no, I'll say this is what we call a hail swath. So you can actually see this on that MRMS product viewer. You can say, show me the hail size swath over the last 6 hours. And so the Huntsville damage is where we have the star there. This storm formed, it was intense, and then it collapsed over Huntsville. So just like Belleville in a way, storm collapses, pushes out a tremendous amount of wind, a lot of damage. There was also another storm that tracked down from Madisonville through other Montgomery County, Willis, all the way down through Conroe. This was a very significant storm as well. Did a lot of damage to some of those areas. So what does this storm look like? Now I'm looking at Huntsville. You've got two updrafts here, one to the west, one to the east. And that's what we see here too. Two storms. Let's focus on the Huntsville one. So there it is a little bit before. There it is over Huntsville. There's some hail there. There's no circulation at all. There's no sign of a tornado. Looking at the Ville in the lower right, we go from about 60 to 50 to 20. All right, so that's an indication that the storm is collapsing over Huntsville. Now with this software, you can actually look at it even a bit differently. You can look at the cross section and you see these high reflectivities up to 40,000 feet. And then 5 minutes later, it's down to about 30. Now the core is hitting the ground. It's actually descending on Huntsville as we talk. They're getting all this wind and hail. And so you can actually see the sequence there where the storm itself is sort of collapsing. You could even do a three-dimensional view of this, looking at the 50 dBz contour, high returns up to 30,000, up to 25, up to 20, and then down to 15. So you can just kind of visually see what's going on there, looking at the data, kind of really digging into more of a three-dimensional view. So we kind of covered a lot of ground, and I'm looking forward to answering your questions. Talking about some of the basics of weather radar and some of the things we look for. What I'm going to do now is stop the recording, and we'll take some questions. So stand by.